Hi, in this video we are going to talk about reactions of shifting order. While we are searching for a kinetic equation for the experimental data that we have, it is often seen that some part of the data fits very well for one reaction order, but another part of the data fits well for a different reaction order. Okay, and especially it happens like when there is a change in concentrations, like from higher range concentration, let's say it agrees for one reaction order, but as soon as it shifts to lower concentration region, then it is like agreeing with a different reaction order. So that is what you call reaction of shifting order. Now let us consider one reaction. A gives R and the rate equation is given as minus Ra equals to minus dCA dt equals to K1 Ca by 1 plus K2 Ca. Okay, so there are two different rate constants involved over here. Okay, generally what happens in this equation, as per this equation, is that if we have high Ca, okay, higher concentration region, then obviously this K2Ca term becomes much greater than 1. Okay, then the reaction becomes independent of Ca. Okay, and we therefore we have a zero order kinetics, and the rate constant, the overall rate constant, let me write it as K tilde, becomes K1 by K2. Okay, this happens for higher region of concentration. If we have low concentration region data, it will mean that K2Ca is now lower than 1. Okay, so in that case, the reaction becomes dependent on Ca and it becomes a first order type reaction. Okay, so this K2Ca term now becomes negligible in the denominator. So we have just K1Ca. Therefore, it becomes first order and the rate constant is now only K1. So let me write K tilde is equals to K1. Okay, so this is the kind of kinetics that is often seen. If you want to visualize through a plot, let me show you. So you have time on the x-axis and concentration of A on the y-axis. Okay, now the plot you get is somewhat like this, that the initial part is zero order kinetics, but as it is slowly reaching towards lower concentration region, this becomes a first order kinetics. Okay, and this shift occurs at some point, say here, where the point of inflection takes place, and this shift is found to be occurring at Ca almost equivalent to 1 by K2. Okay, so this is how the shifting order reactions are seen. Now, to find its kinetics, we will apply the integral method. So we are just going to separate the variables and integrate the rate equation. So the integrated form that we obtain by separation of variables will be ln Ca naught by Ca plus K2 Ca naught minus Ca equal to K1T. Okay. Now, if you linearize this and rearrange, you will finally get a form. Let me write linearizing for easier graphical interpretation, we will get a form ln Ca naught by Ca whole divided by Ca0 minus Ca equals to minus K2 plus K1T by Ca naught minus Ca. Okay, so this is the final linearized form that you can use for graphical analysis. Okay, now if you plot this, obviously what you can see is, let me plot this. So I'm just going to create this kind of graph. Now here I'll plot on the y axis, I am plotting this term. Okay, I'm just writing this term as y. So this is on y axis, and on the x axis I am going to plot T by Ca0 minus Ca. Okay, so this becomes my x term. Okay, so the equation is like y equals to minus k2 plus k1x. So you will have the straight line plot. At y intercept you have the value minus k2, and the slope of this plot is k1. Okay, so this is how you can interpret the kinetics for shifting order reactions. Now this, if you extend to a very general case, so let me write the general case equation. It is very similar to what we have just studied. So the general case will be like minus Ra equals to minus dCA dt equal to K1 Ca to the power, let's say, m divided by 1 plus K2 into Ca to the power n. Now at higher concentration, at high Ca, the order is m minus n, while at low Ca, the order is m. Okay, and the transition takes place at K2 Ca to the power n being equivalent to 1. This is where the transition takes place in order. Okay, so now you can use this general expression to fit your kinetic data. Another form of this general expression, so I'm just going to write it. Another form is like minus Ra equals to K1 Ca to the power m divided by 1 plus K2 Ca whole to the power n. Okay, so in this case also the mechanism of the study is essential to estimate the kinetics. So again there also you can reduce similar conclusions, and essentially these kind of shifting order reactions are seen for cases where enzyme catalysis is involved. So one of the classic examples for this kind of mechanism is Michaelis-Menten equation. So this is like, it's in the more in the biochemical regime that we see this kind of reactions. Okay, let me write mechanism. Okay, so enzyme catalysis. Another example is like surface catalyzed reactions. So say if you have some gas which is supposed to react on the catalyst surface, so for that kind of reaction again you can see these reactions of shifting order kinetics. So that is it for the basic understanding about reactions of shifting order. Thank you.